Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, why don't we get started? I guess for this last session for today, I would like to say Beta, Scoop, Nemmerly, Haskell sort of ties together the four talks here. We have four talks focusing on programming languages and programming issues, programming concerns. The first talk today is by Peter Anderson. By way of biography, Peter is an academic researcher at the Computer Science Department of the University of Aarhus, Denmark. Peter is affiliated with the research group on object-oriented languages and has been researching and implementing programming languages, compilers, runtime systems, garbage collectors, etc. since earning his master's degree in computer science in 1992 from the University of Aarhus. And he's going to be speaking on beta.net and the work in bringing beta to ROTOR.
Yes. Before I start, I'd like to say also that it relates to the coming speeches, but it also relates a lot to the speech by Fabio and the Lua language. You will hear a bit about coroutines again, third time today, I guess, and actually we could have written those slides together. So you'll hear a lot of the same, maybe in other words, so maybe we can gain some of the delay. Beta, I skipped an introduction of the language for the time, and so just a few words. Beta is an object-oriented language, statically typed, compiled. It roots back to the similar languages in Scandinavia. Actually, one of the two designers of Simula, Christian Nygaard, is also one of the designers of Beta. So that said, I'll start by saying what we propose for this ROTOR work. So at the time we gave the proposal, we had a partial mapping of Beta to the .NET platform in the order of Hello World programs and stuff like that. So the first proposal was simply to bring this further and work our way up to at least complete the compiler test suite that we usually use. Furthermore, we have a number of libraries that are used from the language. We wanted to port some of them, the most important ones of them, to run on top of the base class libraries. All of this with the ultimate goal of making the compiler, which is itself a beta program, run managed on .NET and ROTOR. Then we also wanted to work with some graphics, and we already heard about that earlier today. And actually, we decided that there was no need for us to do that because the Views group had already done that better than we could probably do it. So instead, here it comes. We will investigate further how to support things like coroutines in a virtual machine. And as you will hear, this falls naturally out of the work with the compiler. The language mapping itself, I'm not going to go through. There's a list here and on the next slide explaining some of the major language features and how they are mapped. Here in very short form, there's a link up in the corner. When you get the electronic version, you can go. There's a number of extra slides at the end of the slideshow explaining both how a simple beta program looks and works, and how we mapped those simple constructs to the .NET language, the .NET platform. Two things I would like to mention is a thing we call leave restart, which is a kind of a structured go-to mechanism. I know the word go-to isn't politically correct, but the idea is that you can set a mark in an execution. You can have a call chain that can then exit or restart its execution from this mark. And this involves unwinding the stack which the only way we could find out to do that in a verifiable way at least was by throwing exceptions, catching them doing the stuff that we need to do. This is pretty expensive, of course. And then the other underlined item, coroutines, that I'll get back to later on. The Bootstrapped compiler was the ultimate goal of the first part of our proposal. This is, as I hear it, normal-sized compiler source, and we worked on this a couple of months and have it up and running now. And there's a URL where you can go and download it. There's a wrapper script to run it on the ROTOR, and it runs, although pretty slow. I'll give you some numbers a little later, if I dare. First, we did this on the .NET implementations. It runs pretty well. It is a big .NET program running, and if we give it a small beta program as input, it works fine. But if we give it a larger program, mysteriously it breaks with out-of-memory exception. Okay, it uses quite a lot of memory, but not at all that is available. So that's something that we had to investigate further. So this is exactly a place where ROTOR would be a nice tool. So we expected that we could go in, use the low-level debugging facilities meant for ROTOR, and find out why is that exception thrown when it appears that there's still lots of memory available. However, the compiler works on ROTOR. We have tried many cases where the .NET compiler always fails. The exact same executable running on the clicks works with approximately the same memory consumption. Of course, we are happy that the compiler works on ROTOR, but that meant that we didn't really get to the bottom of why this out-of-memory exception is thrown. So, so here's the statistics. If we take the Bootstrap managed compiler and pass the compiler test suites, which is about 12,000 lines of code, into it and do all the stuff that's needed, including calls of ILSM 75 times, we get some numbers. If we do it on natively, we have a native executable on Windows. It takes 21 seconds and uses about 10 megabytes. So hang on. If we do this on system, okay, first this one, yeah, you saw that on .NET. It simply fails about halfway through the compilation. There's a strange number mentioned here, the number of threads. I'll get back to that. But here it is. If I do this on a checked version of ROTOR, we get a nice little slowdown of a factor 350, which is, I didn't see anyone else publish numbers, but I guess this is pretty scaring. But notice also this number of threads that's created through this execution. Actually, there's no concurrency involved, but I'll get back to that, and of course it relates to coroutines. We did try it on the optimized versions of ROTOR, and we get a slightly better performance, but still not very useful in every day. And I don't have the full slowdown because doing these kind of measurements on very small input files for the compiler on the .NET platform didn't really give any meaning. So, but I would expect it to be somewhat better than the free version of ROTOR. I must say here that this has to do with coroutines, and the next slides will demonstrate this. And if I have programs not using coroutines, we have a slowdown of about a factor of 2. So, but I tried to find a tool to. I haven't dared to touch the Visual Studio 2005. But I looked around for other tools that could do some profiling, and I found someone called nprof, and I know you probably can't see this, but if we drag out some of the numbers for a randomly chosen thread, here you can see the top numbers all relate to coroutines, including some thread stuff here, which is also used for coroutines. The percentage used in this run method is 88% of the running time for this thread. So I'm not sure exactly how to interpret these numbers, as I didn't. Actually, this tool does not have a manual. So, but I'm just guessing that this is a clear indication that coroutines are pretty inefficient, as Fabio also told us. As I said, if I do some test programs using coroutines and some not using coroutines, I can clearly see that the measurement, the slowdown coming from coroutine usage is, sometimes a factor of 100 higher than the slowdown coming from just our usual mapping of the language. So that's why we really need to look at these coroutines. And as Fabio already explained how it works, probably I don't have to say much about this slide. But here I have expressed a coroutine in C#. The one you call resume, we happen to call call, and that's difficult to say, call. So I may use the word attach that we usually prefer. But and we have a suspend method. I think you called it that too. Then we have an entry point here called do, which corresponds to a run method in a thread. And the semantics of it has already been explained by Fabio, that you can stop an execution and resume it later on from that point. So, but if some of you never heard about coroutines, I actually prepared about 10 slides that explains it very detailed in C# how tree merge goes on, including animated stack illustrations. And there's a link up here again in the corner where you can go to these slides and see it for yourself. The current implementation of this class is probably almost the same as the Lua implementation, where we have a global variable, static variable, pointing out the currently executing, and we have a backlink to the one that we came from. We have a thread that handles that contains the stack that we need, and we have, in our case, one method called swap that switches between the two coroutines involved in an attach or suspend. The swap method is implemented more or less like this. Some of it is left out, but what it does is that it swaps the pointers, as it says, and then it uses signals and wait to lock on an object, that way to resume and suspend the two threads involved in this coroutine switch. In my slides, there's a complete C# program in the notes section that you can take out and compile and run this example. We also did this on Java, and there it appeared that the allocation of a coroutine is the major problem. Not so much the execution of it, but the allocation. And if you think of it, they probably have a megabyte of stack for each coroutine. And as you saw, this compilation of a pretty small beta program involved 25,000 coroutine instances, each having a thread. So we have an idea that's also the case here, that's probably very expensive and contributes to this huge memory consumption. We didn't really try this on .NET. Instead, we did some other things that I'll talk on in a minute. But I could easily try this optimization, and I think I will after I saw these numbers last week. Another thing is that we have a suspicion that coroutines may stop in a state. No. A coroutine that is suspended may cease to live because nobody really wants to activate it again, and all references disappear for it. So even though it could live on, it should be collected by the garbage collector. We have a suspicion that this is not the case when it's waiting for an object. even it's waiting for itself. So it's not that it references another object, but we have a suspicion that that when it sits in the wait queue for a lock, it may be that it stays alive. At least we see a memory consumption going like this, even though we do see garbage collections. So this is another thing that we'll have to look at. So, as it was mentioned by Fabio, it's desirable to have a more lightweight mechanism. And well, you already mentioned it. There's this yield stuff, but yield is just a state machine that gives you back some values from one level, from one method. You can't, as Fabio also explained, you can't have a method call that issues this yield that belongs to this iterator. So it's not really a coroutine in the classical sense, a full coroutine as you called it. Then there was this fiber. So I have a few more details than Fabio mentioned. For the .NET 1.1, this guy, I'm not going to pronounce it, he made an article in the MSDN magazine where he described how to use the hosting API, and from the source of ROTOR he guessed some unmanaged, some undocumented, in the .NET sense, undocumented methods he could use to actually set this up and wrap those fibers that Windows have and use them as coroutines in C#. And it works. You can download it still, I think. It is pretty hairy, and there are various comments on it on the net, including a lot of Microsoft comments. Some of the guys associated with the CLR team really warned against using this, but on the other hand, they said that it's going to be supported in the 2.0 runtime, except for debugging issues. And Fabio pointed out to me that actually there's a sample included now in the .NET 2.0 documentation at this link. However, when we tried it yesterday, it appeared that, okay, the page is still there, but the sample itself has been removed. And when we then checked this original article, then last Friday, 4 days ago, there was this comment added that this is no longer supported by Microsoft, more or less. So, and we asked some of the CLR guys here yesterday, and they didn't. I don't know if they agreed, but it sounded as if there was a decision to pull out the fiber support in .NET 2 again. So how that's going to end, I don't really know. So originally we also thought that we were going to, again, like Fabio explained, do some hacking of the ROTOR implementation and support it directly. So this would involve something like a swap instruction, which would be pretty straightforward to add. The hard part, again, as Fabio also said, was how do all of this coexist with managed threads, synchronization, exception handling. Of course, we read the Bible about this, and they explain pretty well that the concurrency model is not the easiest part to work with. So, yeah, to be honest, we thought this is too much to start with, and I heard somebody else saying yesterday that they had too high ambitions, so I'm glad that we reduced our ambitions for a while. So we simply needed to do some pre-study on a smaller VM. And then it happened to be that on our university there's another project which on the same floor that related to a European Union project, which has a virtual machine called pre-VM for Palcom runtime environment. This is a simple, dynamically typed, speaking of dynamic typing, interpreted runtime system with less than 20 bytecodes. It's currently implemented in Java, but we are working on re-implementing it in C++ to use in small devices. like the .NET, even though it's dynamically typed, we have built language mappings for statically typed languages like Beta and Java, and of course Smalltalk, which fits pretty well into this. The reason it's interesting is that this VM is solely coroutine based. We don't have threads in it. The thing that the VM understands is coroutines. Coroutines can be scheduled by the programmer himself. The system has some default schedulers, you can replace them. This means that you can have all kinds of scheduling strategies that you implement yourself, even hierarchical schedulers. Then if you want something like threads, you can do preemptive scheduling of these coroutines. And I have a slide here, no, the next, explaining that. So the coroutine is defined by the VM simply as a stack with a backlink and the current instruction pointer, more or less. The handling of this coroutine swap is simply through instructions push the coroutine to attach or suspend and do the swap with another bytecode. And then, what about preemptive scheduling? Well, this goes on this way. There's a way to set up an interrupt interval. You can set up a handler, and this is dynamically typed, it only needs to have, it can be any object as long as it has a method that implements the handle method. And then when this is called, you can suspend from the outside the currently active coroutine and attach the one that you think is going to be the next, depending on the policy of this scheduler. These interrupts are not real interrupts. It's more like timeouts where there's a flag in the system that says that now it's about time to begin looking for potential interrupts, and then we have save points in the code where these checks appear. It's completely the same as in the ROTOR implementation. There are save points where GC can happen because they have to stop all the threads. Synchronization happens with a single primitive, a single log primitive, and all the classical abstractions for synchronization can be built using that. As it is, we don't need any special bytecode for implementing the log, but we may have to insert more of these interrupt places in the bytecode, and that may force us to implement a test and set bytecode, which, by the way, is pretty easy to do. A very special thing that I just want to mention, but that's a little hairy actually. If we have an I/O call out of the VM, we are considering two approaches on how to handle this. The current version actually does, what it does is well, you get blocked. There's this interrupt, and this means that now we should not stay here any longer. So, but actually it's the VM that's blocked at that moment. So what we do is to leave that alone, make a new native thread, put the VM in there, and reschedule from where the VM was. And then when this I/O call finishes, it just forgets about the rest of the VM execution that was going on over there. So that's a way to optimistically assume that it will not block this I/O call, but if it does, we put it aside. Another way would be to make the programmer more aware of which one can block and not block, and then have a traditional worker thread pool to handle these I/O calls. This is the way that coroutines are meant. The semantics of coroutines are meant to be in beta. Like in Lua, we do not have threads in the language, but we have syntax and semantics for coroutines. So that's why this fits so well with beta. And of course now is the question, and I haven't answered it, how this is going to map to ROTOR. We're still pretty much work in progress. This European project is 4 year, and we are on the 2nd year at the moment. But it looks pretty well, this strategy. We have a very simple semantics for coroutines. And for instance, this problem I mentioned with whether we didn't know if the built-in schedulers of the system kept coroutines alive, although they were not referenced because they were hanging on some lock or something. That can be easily controlled by the guy who wants to schedule these coroutines, since he can write his own scheduler. He more or less should write his own scheduler. So it's up to him how to handle this special problem. Of course, it introduces a number of other problems. For instance, if you have different scheduling policies in different components, how do they interact? It's a bit like the original problem of how to make coroutines coexist with threads in ROTOR. It's two different worlds, so to speak. So it's just a simplification of the world to do it this way. And as it is, we are not sure how much of these ideas can be used on the ROTOR platform. We didn't start an actual implementation like I heard Fabio mention they just did. But what we do hope is that as we are now working on this embedded C++ version, which in many ways resemble the way that the implementation of ROTOR is, at least we'll get used to walking around in a space like that where you have an implementation like ROTOR, and I think then at least we will then be, so to speak, dressed to jump into ROTOR and try out whatever we can get to work there. And then there's this dark horse called the Fiber API that I mentioned, which sometimes is available in 2.0 and sometimes not. But if it is, of course, we can use that as I expect it to go into ROTOR also if it gets into .NET. So here and now we are expecting to do some obvious optimizations like this thread pool I mentioned for the current C# implementation of coroutines. The other VM that we have been studying, we will learn a lot from that by completing that implementation. We were previously in contact with some guys in Cambridge that did some of this for a Java VM that, unfortunately, it was a commercial one. They couldn't show us, but we have contacts in the C# team. One of my colleagues just got hired by Anders Heilsberg, who also is Danish, and within the CLR team. So we might get back to a closer cooperation, and of course, as I just learned about this Lua project, I suggest that we have some talks about this. And .NET 2, well, let's see. So that's pretty much it for now. Any questions?